Hi, this is Phil Kerner, the Tool and Die Guy, and today's lesson, plastic pants, the space shuttle, and a classic. All right, so what do I mean by that? Well, first of all, let's get started with some real manufacturing, right? A real life manufacturing lesson. I know you guys like this. So here's a fixture that kind of came across my bench today, and I've been holding out on you guys. I actually have a new apprentice, trainee, kind of working with me. Now, he's a really good kid. Really like this guy. But he's like 8 weeks and 3 days into the trade. He came to us through a job training program, and he aced his math test. That's why I got into that. So they gave him some blueprint training a little bit. He's never touched a machine before. So it's up to me to break this kid in. And he's really good. Like him. Very earnest, sweeps the floors when nothing else to do. Good guy. But so this fixture came across again my bench today, and he's looking at this thing. He's staring at this thing, and he kind of glues in on these two threaded holes here, right? These two tapped holes, quarter 20 UNC 2B and a 632 2B. Okay, so he's what's the 2B mean? Well, I said, great question, right? I said, here's the deal. This is a fixture for our plant. And whatever tap I have is going to be fine, because I know we're just going to bolt a clamp in there. But I said, if this was a part for a customer that we were going to ship out, we'd have to work on that, make sure we got the right tap. So the big question is, I'm looking at this fixture today with these tapped holes. Is it 2B or not 2B? And that's why you're here. So because I had to say that. I just had to say that. I'm going to show you a picture of the fixture it was done. And there you have it. Pretty cool little guy here. These are these Mighty Bite fixtures, and what we did was milled these profiles into these gold-colored aluminum clamps. And there's, in the one end here, you can see the part we're going to hold. These wedge-shaped parts. And what we have to do is face them off. We've got like 1,500 of these to do. So that's a quick way to do it. You clamp down in the middle here, and it pushes them against the sidewall and bang them across, across the top. They'll be perfect. So that's today's real life manufacturing thing. Here's the lesson. Here's the pickup for the whole deal. So the operator can just pick up on the center hole, like working from center. Okay, so that's a fixture I built today, and to be or not to be. Okay, so plastic pants. Let's go. All right, 1995. These are some stuff, some plastic pants for the Little Tykes company. And I can't quite figure out where the head went, but anyways, that's what I built. And by the way, in the background, it's a really cool Mark's Toys train set back there. That was mine when I was a kid. Kerner Tool and Die built that for Mark's Toys here in Erie back in the 60s. So plastic pants. Well, how do you do plastic pants? Like that. See, what you're seeing here, and for all my mold makers, are these very fine beads of plastic around here. All right, and what those do is when they put these two halves together, they hit them with a thing called a horn, which is just it looks like a die, and it's called a sonic welder, and it puts an ultrasonic sound through these two parts and welds them together. It literally welds them together. That's why, for all you dads and moms out there who can't get plastic toys apart, that's why they're not glued together. The plastic's been melted together. But the point is here is look at these electrodes to cut those beads. All done without a CNC machine. Really. So how do you do that? Well, let's keep going. There's a space shuttle. That's the real space shuttle. That thing they show you on TV all the time. That's like the moon landing. It was all fake, right? So that's the real space shuttle. I think that's John Glenn, and that's the parting line for that particular pair of parts. Look at that big lip in the front, and again that sonic weld bead all the way around. No CNC machine. So here's the electrodes for that. They're a little chipped up now, 30 years later, but you can see the fine detail there. So how do you do this, right? So again, this was one of the hardest molds I ever built, a plastic toy lawn chair. And that thing was only 3 inches tall, 3 or 4 inches tall, and but you should have seen the parting line on that. Again, all done without a CNC machine. And finally, this plastic fish. This is a 10 cavity mold, and they were numbered eventually 1 through 10. And this is for kids. They try to catch the tail, but look at the parting line. Okay, all that parting line done without the benefit of CNC. So how did we do that? Well, we did it with a KF12 decal. The only difference between the KF12 decal and the K1 decal is these two tables on the KF12 have a power feed that'll feed them both up and down at the same time. If you don't have that, you have to crank them both up individually. So the KF12 was the real model to have. And of course, if you're going to have a decal, you have to have a decal SO tool grinder to grind your styluses and your cutters. You know, I have to say, I loved running a decal, and that's me when I first got started. I was still working my full-time job at Tetra Tool Company, but at night I'd go over to this little spot where I'd bought a decal and would make these little forging dies for Kuhn Tool. And you guys might remember Kuhn Tool. The Clearview radius dresser that they sell or Herman Schmidt sells is built by Kuhn Tool right down the road from us. So there I am. There's your pattern on the right, and there I am tracing it into the steel. And eventually, I would get a pair of these done. And back in 1995, what do you think I got paid for those two things? About $750 for 3 nights' work. And it wasn't until midnight. A couple nights, 2 hours a week. And that's how I got Kerner Tool and Die started. Eventually, I would end up owning 3 decals. And the tan one was always in the middle, and then a couple other ones. And kept those running all the time. A great story behind that is there's a young man that worked for me named Kyle, and he did a really good job on the decals as my apprentice. And he went on to become a really terrific 3D programmer. And he told me, you know, last year we were chatting, and he said all that decal experience, learning how to do it manually, made him such a better programmer. Back to the whole thing. It's always good to learn a little bit manual stuff first before you go to the CNC. And now for today's lesson. Well, you guys have made it very clear to me you like the old stuff and the new stuff. So you just saw the old stuff. Hope you appreciated that. And the new stuff. Well, the new stuff isn't so new tonight, but it's new for you guys. About 2012, November 2012, when I was running my membership site, I recorded this particular video. And the whole cadence of this lesson is going to change a little bit because this is a different format, video format. But it's 15 things I do on every job. When I get a new project or job, what I look at. So this is really good information for you guys. And I'll tell you right now, at the end of this video, it's going to say, just click on the video link at the end, and there's going to be a free PDF download. I can't find it. It doesn't exist. So just pay attention or rewatch it several times. It's going to be up on YouTube forever. And but these are 15 things I do when a part comes across my bench. I think this will be really educational for you guys, especially for you newcomers. What I think about and with my experience. So with that being said, you got something old, you got something extremely funny tonight, even though my wife didn't get it, and then this lesson. So I hope you enjoy it, and let's move along. It's Phil Kerner, and welcome to the Tool Room. And this is going to be a really great video presentation for you guys to get some basics under your belt. And things you might not think about, and my main job is to A, keep you from scrapping parts, and B, help you get a better understanding of how somebody that's been doing this for a long time does it. All right, now does that make me any smarter than you? Absolutely not. It just means I've been doing it a lot longer. Okay, and you can learn this stuff much quicker than I did because you've got me. So let's start a new job or a new part, and whether it's something that your friend handed you and said, can you make this part in your garage or your little hobby shop, or you're starting out in a trade. And what do I think about when I get a blueprint? Somebody hands me a part or a blueprint. Well, starting a new part. Let's go through the process here. And I think I'll do a companion video to this down the road where I'll actually get a printout. I got to be very careful there because I can't be pulling prints out that are, you know, copyrighted or trade secrets. So I've got some prints I think around where I can maybe go through it again looking at a print, but this will really help you a lot. So let's start a new part. First things, 15 things I look at. 1, overall dimensions. It's shocking how many prints I get that just don't give me that the part is 3 inches wide by 6 inches long by 1 inch thick. No, they dimension it from this hole to this corner to this hole. You know, if you're an engineering student, and I hope you are listening to this, don't do that. Give us an overall dimension, a finish height, length, and width, because we really need to know that. And why we need to know that is we need to know right away if that'll fit in our machine, and what kind of part are we looking at. And every time you make me do math, you're risking a scrap part. And what I mean by that is if I have to add up 6 dimensions to get the length, the chances are really good. Every time I'm pressing in numbers, I could make a mistake, and especially if they're metric and I'm converting them. So always, 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 you need to know the length, width, and height of your part. Okay, that's the first thing I think about. Second thing, not a big deal, but how much does this sucker weigh? Do I need a crane? Do I need a magnet? Can I lift it? And that's important to me because I come from the mold industry, and a lot of my pieces of steel I worked on weighed 500 to 2,000 pounds. So when somebody hands me a part still, I look at it, it's okay, I can lift those, or I might need a hand lifting them up, or I might need an eye bolt put in it to just lift it up on to the machine or into the lathe, and I might need a magnet to grab it if there's no holes in it. So I just like to know the weight. That's a quick thing. It's not a huge thing, but I always think about the weight. So can I lift it? That's a big deal. Quantity, big deal there. Am I going to be able to do this in a vise? Should I set up a vise stop? If I'm doing more than 1 or 2, it's time to start looking at some stops or some fixturing. And if I'm just doing 1 or 2 parts, again, I can indicate each one in, pick the edge finder up. It's not worth building a set of jaws or a fixture for 1 or 2 parts, in my opinion. But or if it's a more complicated part that needs to be located off of a hole or something, you've seen me do this in some of my other videos. Maybe I need a simple fixture of ice jaws, but what I will tell you is not always necessary, because if you're only doing 1 or 2 parts, it's usually not worth the time. You can usually just do them separately and you won't gain any time by building a fixture, okay? Will it fit in my machine? Well, you know what? People every day put things in machines that they don't belong in. And if you've been in the trade a while, you're laughing already, because that really does happen. People come over and assume because you've got a 20-inch by 60-inch machine table, you can do a 20 by 60-inch part. Well, sometimes that's true, sometimes it's not. Sometimes the table doesn't always have the same travel in the X and Y that the table size is. So, again, you can do parts in your machine that are too big for it, but you have to factor in that you might have to rotate the part or move it around 2 or 3 times. Adds time to it, and you need to think about that ahead of time. If it doesn't fit, what needs to be done first, so I don't paint myself into a corner and end up doing something I shouldn't have done. Now I can't figure out how to get back to where I was. So it's a simple question, but will it fit into my machine? Tolerances. What do you do when you look at a hole that needs to be located within 1/10? Can your machine do that? You just need to remember that people throw tolerances on IC prints all the time, and I think the tolerances are way off. I've seen holes that had to be located within a few tenth of a thousandth of an inch, okay? But the hole diameter is plus or minus 10 thousandths. Absolutely crazy to me. I don't know why you need a hole to be located perfectly, but it can be 10 thousandths too big or too small. It makes no sense to me, but you know what? That's your customer, and if you send that part back to them and it's not exactly where they wanted it, even if the hole's the right size, it's going to get rejected. So tolerancing is a big deal, and I always look at that. That's one of the big keys. If you're looking at new products and new drawings, watch those tolerances, because it'll tell you what you got to be careful with. This is one that's very important that I tend to overlook sometimes: surface finish requirements. And why that's important is you have to know how to hit certain surface requirements. A drilled hole is pretty rough. Milled surface, yeah, I can get a nice surface on a mill, but not as good as a grinder. So watch those surface finish requirements. And again, we'll go through a print and I'll show you what they look like. But I still get caught by surprise once in a while when they want a surface finish. Not very often, but occasionally it'll bite me. So just make sure they're not calling for something honing-wise, lapping-wise. Again, it doesn't come across a lot, but if it does, you can't just drill and ream that hole. You might have to make allowances to lap it when you're finished. So again, lapping, honing, grinding, or polishing are some other things you may have to do to a part. The surface requirements are very important. threads, whether you're on a mill or a lathe. You know, most of the time we can just tap a thread, run a tap through it, and it'll be fine. You might have to check it with a gauge, or sometimes just a bolt. If the bolt goes in the hole, you're probably good to go. But there are thread gauges. Now, the question is, when you see a tapped hole or a male on a lathe, you know, is a tap good enough? What's the tolerances? Or does it need to be formed by either turning the threads or thread milling them? Or in some weird cases, they might have to be ground. And that doesn't happen very often. And another thing to consider, metric. These metric taps. A lot of shops don't stock metric taps. So do you have the gauges to check it? English or metric dimensions. English or standard, as you can call it, or metric. You know, again, I get prints every day from a major manufacturer. They're in metric. And I have to sit there for an hour and recalculate every dimension to standard or English. I don't like doing that because it's not hard, but dividing every dimension by 25.4 sets me up for a disaster because I usually get parts that they only want one of. So I have to double check everything I do, which you should too. But boy, if you're sending your work to a shop that only works in that's in America, you might as well can reconvert it for the guy. So again, every time I have to pick up my calculator and figure out what you meant, Mr. Engineer, you're risking a mistake. And I know that's what you pay me for, but that's what we pay you for. Give us good drawings. Sorry, I have strong feelings about that. What's the material? You know, different materials can cause a lot of heartaches. And as I've said in some of my videos, you guys will tend to end up in shops that tend to either work with this type of material, that type of material, and they have it down to a science. But the place I work, 80% of the stuff I get is pretty much the same every day, but every once in a while they'll throw in a piece of stainless, and I get lazy and I don't notice that on the print, and down comes the drill and squeak, 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 no point left. Oh, God. So, because what we do at our shop is a lot of times they saw the material off, and they'll throw it in a tumbler. And a tumbler is just a bunch of stones with a sort of slurry in it that takes the edges off, and what it does is turns everything silver. So everything in our shop looks like stainless. So when they hand me a piece of stainless, it's like April Fool's Day. You know, and after I blow up a drill, I realize, oh, these 3 parts are stainless. So take the time to know what material you're working with and get the right surface speeds and feeds, and realize if you're working with a pre-hardened or stainless steel, you're going to have to slow everything down, and that does add to your time if you're quoting work. Heat treating. Is this part going to be heat treated after I'm done with it? Well, if it is, do I have to do anything after heat treat? Because guaranteed, unless it's being very lightly heat treated, where they're not going to really turn this part red, your part's going to deform. Maybe it'll be intolerance, maybe it won't. It's not uncommon in the mold industry and dye industry. You know, you leave stock on everything and grind everything after heat treat. So just remember, heat treating does throw a fly into the ointment here, and you should ask, is this part going to be heat treated, and will I be okay to finish the dimensions as I go, and not worry about allowing for having to come back and remachine this part after it's been heat treated. Can my equipment hold these tolerances? Wow, great question. You guys with the garage shops and the Bridgeports, you know, you're probably laughing at that. How many times, or even if you guys are working in a shop, you know, your boss, brilliant as he is, goes out and gets you a job to do on a Bridgeport that's 58 years old, and he wants a tolerance hell that you can't hold. Just can't do it. And people who have never done this don't get it. But I have a machine that I run every day that can't cut a round circle with a mill. I have a way around it where I can get it close, but because the ball screws are a little worn out, I'm plus or minus 1 is the best I can do on a 2-inch circle, internal or external. I'll get you to actually plus or minus 1. If you want 2 inches, you'll be anywhere between 2 inches 1/1000 and 1 inch .999. It's just the way it is. What I do is I climb mill it and conventional mill it. That seems to take the backlash out. But again, when they want me to hold something to 2/10, I have to bore it or send it to another machine if it's an external, because my machine's just too old. It's 20 years old, no complaints there, but I know what it can do. So you need to know what your equipment can do. Don't paint yourself in a corner by saying, I can do that job, and then because you didn't follow my other steps about tolerancing, find out, oh my God, I can never hold these tolerances on this machine, okay? How's the material going to come to me? Is it going to be saw cut, milled, ground? Do I have to square it up? Those are all good questions to ask, because if it's supplied to you just saw cut or rough, you got to figure out how to hold on to it. Okay, in the next video, I'm going to show you how to really square up a block from a very rough stage. But very good thing to know. How's the material coming to me? Again, leaving stock for other operations. Do I have to leave stock for wire EDM? Do I have to leave stock for grinding? Do I have to leave stock for lapping, honing, polishing, any of that? Just a good question to know. Again, grinding, etc. Any special tooling required? Taps, inserts, metric tooling, extra reach tooling. You know, you got a deep pocket to cut. Good thing to look at right away and say, hey, Mr. Foreman, I need a 14-inch long drill for this. What do you mean you need a 14-inch long drill? Yep, part's 14 inches long or 13 inches long. They want a hole drill. Oh, they didn't see that when they quoted it. Remember, don't paint yourself in the corner. Look at little things. And again, I don't expect you to remember all of this, but there's a list at the bottom you can download too. But that's a nice checklist. Make sure you've got the metric tooling or long reach tooling or weird size drills you need for the job before you're all set up, moving along, and then come to a screeching halt. And you need to get them ordered right away. Don't start on the job until the tooling's sitting on your bench if you can possibly do that. And then what do I need to check my work? Number 15 and last. Do I need special pins, gauges, special mics, thread mics, digital mics, 16 to 18 inch outside micrometers? Sometimes you need more dimensions from the engineer, and you need a reference dimension. Hey, what is it from this edge to the edge of this hole? It's so I can check it. So that's another thing. Look at your prints and realize this is a 2-inch hole. It's 2 inches, 22. Well, my mics only go up. My inside hole mics only go up to 2 inches. Our pin gauges only go up to 1 inch. So how am I going to check that hole? You need to think about that. And those are little things that can bite you later. So those are 15 little things I do every single day, kind of in that order. In my case, they kind of go through my head very rapid fire because I've been doing this for so long. And again, at the end of this video, you'll see this list is a PDF you can download. And the next video, what I want to do, I think, is get out a print and start going through a print. But hope this kind of walked you through my process. And welcome to the tool room. I'm Phil Kerner, and we'll see you on the next video.